All right. So let's talk about exam very quickly. I don't want to spend a lot of time here because we have a full exercise ahead of us, but I do want to tell you a little bit about the structure. First thing is whatever is your campus, you should go to your own campus computer lab location. You cannot do the exam remotely from our office or from elsewhere. It has to be on your own campus location. I just want to get that very clear. I know, I mean, if you are, those here in Athens, I think you all know that this is the location because you've been coming to class in person. Those of you in Griffin and Tifton, if you do not know where is your computer lab location, reach out to us or maybe check the syllabus. It's also there, but make sure you know because you have to go there. Second point is it is closed book. You will not be allowed to use your own laptops. It's going to be, the exam is going to be all on ELC, but you will need to use the computer right in front of you, not your own laptops. So remember that. You're not going to be asked to code. So there's nothing code related that would require you to have packages installed or to installed and all that, which does not mean that there's not going to be questions about code. So I may ask you, what would be the function that you would use here? Or maybe what is a key argument that we always changed that we need to change for this purpose? Things like that are fair game, especially with things that we do a lot. I'm not a tricky professor. I'm not going to ask you about a function or an argument that we've used once. That's not going to happen. I'm going to ask you about things we use every time. Anything I ask you in class and I prompt you all in class, those are really great questions that I will include in exam. So things like that are what I really want to see that you're understanding, that you're creating this understanding of how to use, when to use, what you need. And I will not ask you to fully develop a ggplot code, for example, right? I may give you a ggplot code, hide away some parts of it and ask you, what would you fill in the blanks, for example, right? I don't want, like I think after a lot of time working with R, then you start maybe remembering things from head, but I do not expect you to be able to remember a full code from head. I mean, we have Google, we have Stack Overflow, ChatGPT for those purposes, right? I don't think that's a skill that I believe is what you need to master is memorization. I want you to understand the concepts, to kind of have an understanding of what you need to do certain things, and that's the extent of it. Anything that was in a quiz, anything that was in an assignment, anything that was in a reading material is fair game. Anything that was in a lecture is fair game. As you also know, I add a lot of instructions and text in the scripts. So don't only pay attention to the code itself, but also if I have like interpretations or maybe an introduction to something or maybe an explanation of something that is in a script, that is fair game. You're going to have 2 hours to complete it. Again, you don't need anything else other than the computer in the computer lab in front of you. It's going to be through ELC. And the content that goes into that exam is what we finish on the split plots. So split plot is the last content. Today we're going to be covering regression. That's not going to be part of your final exam, or sorry, of your midterm exam, just so you're aware of it. Okay, yes.
Two questions. First one, when is this?
So the exam is on Thursday, next Thursday,
A week from.
a week from today. Yeah.
And my next question is, are we gonna be able to, like, are the quizzes, can they be open so we can study on them, or are they just gonna?
So right now you don't see the quizzes?
Um,
Okay. Yes, they should be. So you shouldn't be able to answer again, but they are going to be open. Yeah. So if they're not yet, I'm going to make them open.
Okay, all right, great. Thank
Yeah.
you.
And also just a heads up. So Arminder has working a lot on grading everything. I'm going to take a look at all the work he's done. And my plan is to publish all the grades and the feedback by tomorrow. So you have that to study as well. What you're going to see is normally we only tell you if you lose points. And so if you lose points, we're going to say on question X, you lost points because of this, because you did not say this, or because you said this wrong, or because something was missing, whatever it is. You're going to get, I guess, a feedback on why you missed points and not necessarily when you did a great job. So if you did not get feedback on a specific question, is because you got that right. What else I wanted to say? Let me see, I have a to-do list here. Okay, so grades, exam. So something I do want to mention to you all, which I think was already clear from the beginning, but I just want to remind you, is participation is 10% of a grade. If you do not participate in class, if you don't participate maybe on the office hours that Amrinder has, or maybe on GitHub asking and helping others, then your grade starts off from a 90%, basically. So please don't let that happen. It's easy for you to get participation. A lot of you are participating. I really appreciate that engagement. If you don't like speaking in class, make sure you use GitHub for that. I don't want you to feel uncomfortable, but at the same time, I need your participation, right? So if you have not participated as much, make sure you change that, because otherwise, when I'm going through participation points, I'm gonna have a sheet of, has this person asked or answered in class? Has this person asked or answered on GitHub? If I say no to both for you, you get a 0 out of a 10% of your total grades. So it's easy to not get a 0 there. Just make sure you do participate to some extent. All right. Any other questions? Okay, so we're gonna put a pin on exam topics and conversation and start working on our exercise of today, which I'm very excited about. I think it's going to be a really cool one to go through. All right, so assuming you were all able to do the setup and you're ready to go, then if you don't have yet your 07 reg project open, make sure you launch that on your side. Let me see. Am I sharing my screen online? Are those online seeing my screen?
Yes, Dr. Bester.
Yes.
Perfect. Awesome. Thanks. All right. So we're gonna go on our code subfolder and launch that script so it shows up on the side. Put myself up here. Also. All right. So up until now, we've been talking about analysis of variance, right? That's all that we talked about. So we talked about completely randomized designs, randomized complete block designs with block as fixed and random, and then split plot design. Today is the first time we're going to be talking about regression, which is another very common analysis in agriculture in different areas of really any area in research. It's one of the most commonly used analysis types. So you could do regression for different purposes. Today, my purpose to you is to show you basically how can we apply regression to find an optimum level of a given input that optimizes a given output. And then the data we're going to be using here comes from a well-conducted randomized complete block design. We're going to try out 4 different models. So the way that this works is, so the example we're going to be looking into is if you have seeding rates and you want to know what is the seeding rates that optimizes yield of a given crop. If you're not in crop and soils related research, and that does not make a lot of sense to you, think of it as far as, if you have this whole room here and you put one plant of whatever it is, let's say it's a corn plant. That plant by itself is going to produce a lot because there's no competition around it. However, on an area basis, it's not very efficient. We're using this whole room for a single plant. The other end of that spectrum is to have 1 million plants in this room, where they're all stacked together very closely. At the level, there's also a problem because now competition is so intense that no single plant can be productive enough. So there's a trade-off between how many plants can fit into this room in a way that we optimize the area of this room that we optimize production of the entire area of this room, which is basically yield. So this is a case that is very common in applied agronomy studies where you would want to see like how many plants can I fit into this room before competition gets high enough that yield starts to decrease after that point. So that's the type of study we're going to be looking into here. And in these types of studies where you have a numerical input and you're trying to see what level of that numerical input optimizes a numerical output. So numerical input, seeding rate, numerical output, yield. When we have those types of studies, I want to be able to say, I optimize yield with X number of seeds per hectare, for example. And if I go above beyond that point, I lose yield. If I go lower than that, I lose yield as well. And whenever we're trying to find these optimum levels, really the way we're going to do this is fit different models to that data and see what model is a better fit for the data we have, and then use that model to then determine the optimal level. That's what we're going to be doing here. We're also going to be using Bootstrap to create some confidence intervals around regression lines. And then, so we're going to be running here an intercept-only model, a linear model, quadratic model, and a linear plateau model. And we're going to be comparing all these models using AIC. So AIC is a Keikis information criterion. It's just one way that we have to compare different models that are being fit to the same data. And then we're going to use whatever model we select in the end, we're going to use that model to find the optimum level of seeding rate that optimizes crop yield. All right, so quick intro here would be, I think what we just talked about as far as trying to find the best level of the input. And really what I want you to think of on your own areas of research is this setup of having an input that you change the levels and you have an output that you observe how that responds is very common across all disciplines, right? So in agronomy and crop and soils, so right now we're talking about seeding rate being our input. It could be anything else that's an input. It could be fertilizer rates. So we talked about potassium and nitrogen, could be other fertilizers. It could be any pesticide. You're trying to find the best rates of a pesticide to control a given pest. So maybe a pesticide becomes your input and then control becomes your output. It could be irrigation volume as your input as well. Perhaps if you're not working in outdoors type of research, perhaps you have a controlled environment where you're changing temperature and air humidity and things like that could impact your output. Perhaps in food science could be temperature, could be pH, could be, I don't know, the concentration of a given antimicrobial product. Something like that you're changing the input levels, expecting a change on some measured outcome. Could be maybe control of something, could be yield, it could be other metrics that you're interested, right? So even though we're going to be seeing an example of very applied to row crop outdoors research, but I hope you can see these parallels and understand that in your area, you also may have something that is applicable to you. So because both our response variable is numerical, so response variable is your Y variable, is what you measure, right? Is what you're interested on. So previously we've been doing yield as our response variable. Today is also going to be yield. So because our response variable is numerical and our explanatory variable is also numerical, in this case seeding rate, we can do regression. So regression instead of ANOVA. However, I do want to take a quick moment here for us to realize if I wanted to run this study as an ANOVA, I could, just like we have done with the previous exercise. The only difference then is that instead of allowing seeding rate to be numerical, I would have to treat it as categorical. I would have to set a factor and then get the means of those treatments and not just a regression over those levels, right? So I do want you to understand this, that really for regression, both your X and Y have to be numerical. For ANOVA, at least the ANOVA models that we saw, most of the time, your Y variable is numerical and your X variable is categorical. Now, let's say in this example here, if we would have wanted to do ANOVA, all we had to do was just to treat seeding rate as a factor, as a categorical variable, we would be able to run ANOVA as well. However, let's think on the flip side of that. So let's say that you had yield, explained by variety of a given crop, for example. Like we have variety A, B, and C with different yield potential, for example. You could only do ANOVA, right? Because there is no way you can transform a name into a numerical variable to do regression. So if your X variable is actually numerical, you can do either ANOVA or regression depending on your goal, on your objective. If your X variable is already categorical, you can only do ANOVA. You cannot do a regression with name, right? So I just wanted to make that connection here for you to kind of bring together this concept. I want to show you here a figure that I actually forgot to move into my data folder. So let me do that very quickly, and I'll show you that for us to talk about. Okay, so this is just a figure I can share with you later if you wish. But I'm just bringing that here so we can look at it. So there are many formulas or many mathematical equations that we can use to describe the relationship between a numerical input and a numerical output. I'm showing you here 4 that are very common. There are more than these, and maybe in your specific area, there will be even different ones than what I would use in my specific area, but these are some very common ones. So for all of these 4 plots I'm showing you here, we have seeding rates in 1,000 seeds per hectare on the x-axis, and we have yield in megagrams per hectare on the y-axis. I'm showing you here 4 potential ways that seeding rate and yield are related. For example, let's start off with the first case here. So this is the intercept only model, which would be the best fit if you see no effect of seeding rate on yield, meaning you are increasing seeding rate on the x-axis, yield is remaining relatively stable. One thing that I want to make a distinction here is, so in my research, we do a lot of fertilizer research. So our X variable is normally nitrogen rate. With nitrogen rate, you could apply no nitrogen and still have yield, right? It may not be the best yield, but you still get some yield. With seeding rates specifically, if you apply no seeds, there are no plants, right? So then there's no yield. So in this specific case of seeding rate, it's more something that you need at least something to get plants growing, because you have to have seeds to have plants, and then measure the yield effect as you increase the seeding rate. Having said that, I want you to take a quick moment, and I'm going to ask some of you to help me understand here. If you're looking at this intercept model, and you have to tell, and you know that you did this study on a farmer's field, and you have to tell that farmer for that, if this is the relationship that we'll always see in that field, which may not be true, but just assuming that this intercept only model is what happens on that farm for whatever reason, and that farmer asks you, how many seeds should I plant to optimize yield on my field? And you know that they have that intercept relationship, what would you respond? Well, so this is seeding rate, right? So I guess the fertilizer example was just to give an idea of having 0 being a possibility not in that study. Here, 0 is not a possibility, right? So we're just looking at this and thinking, if this is the relationship for this farmer, how much should they apply? So we have 2 hands here. Let's go. I think Charles was the first one. So let's go, Charles, and then we'll go to Jonathan. Yeah.
So I would advise, and based on the intercept, I would advise them the least.
The least. Perfect. So Jonathan, were you going to say that? Okay. So let me ask you, Jonathan, then a follow-up. Why? Why would be the least?
Cost money. When there's no yield increase, there's no need to spend more money.
Perfect. That's exactly it, right? So here is basically an input, and all inputs have a cost. seed and fertilizer are normally two of the most important costs for a grower's budget. And so, yeah, if you can get the same yield applying 40, why would you apply 120, right? Like your yield is not changing, but then there's maybe this other component here of the economic aspect, which we're not directly looking at this plot, but you can imagine that if you're increasing an input, that has costs, and if you can apply the least and get the same yield, that would be your most economical outcome. Perfect. Awesome. So and this happens maybe because of the crop type itself. Maybe it's a crop that really is very plastic and can really, like if you plant one plant, that one plant's gonna really produce a lot of biomass. If you plant many plants, they will kind of compete and self-regulate how much each plant can grow and produce. Some plants do this very well, others don't. So it's something that's related to the plant type itself, also perhaps to the environment. Maybe this was an environment that was very delimited already, in which case maybe we would not see this response. Maybe it would be a negative response, but it could be related to the crop. It could be related to the environment or to the management. There's a lot of things that could be important at play here, but this is a very common thing that we would see. All right, so let's go to our second case here of the linear response. So what we're seeing here is that each increase in seeding rate in this case is having a relative increase on yield as well, right? So each unit of seeding rate increases is increasing yield as well. So if this grower asks you, what would be the best seeding rate for my field? What would you say? And perhaps let me go online a little bit and see if anyone online would like to say something. Yes, Sabir. Yes, Sabir, go ahead.
Okay, I'll say the highest.
The highest. Why was that?
Because it's any increase in seeding rate, it produces a proportionate increase in yield. So as you keep increasing the seeding rate, your yield keeps going high.
Right. Perfect. Yes. So without considering economics in this point, because it would depend. Really, a full economic analysis we would have to know the price of grain and the cost of seeding rate to really do an economic analysis. But at least agronomically, which is optimizing yield, I agree with that, right? So we would recommend the highest seeding rate because that's the one that's giving you the highest yield. Normally, when we see something that responds like this, I believe for everyone that is in this class, it's probably because you did not have high enough levels on your input variable. So if you see something like this in your research, it's probably because maybe if you added higher seeding rates than what you had in your study, you would eventually find a plateau. Because we're all working with biological systems. There's no biological system that will continuously increase outputs given inputs, right? We will reach a plateau at some point. So, however, it does not mean that you wouldn't see this in research, right? I see this a lot in our research. It just means that maybe that year I could have applied even higher rates of fertilizer and get even more yield than what I did. That's kind of how we would interpret this. However, let's say that you did apply a high enough rate of inputs that you did find, I'll be with you just a second, Shakir, that you did find a plateau or a maximum point of that response. Then we have, I'm showing you at least two functions that could be used for us to inspect the relationship, which is the quadratic and the linear plateau. And before I go into more depth, I just want to give Shakir a chance to ask a question. Yes, Shakir.
Actually, it was for answering the question. I didn't have a question, so.
Oh, okay. Well, I don't know if I asked already, but so maybe you're thinking ahead, but yeah, I'll ask a question here in a second. So these behaviors are very typical if you had high enough input rates that you did find the biological limits, which again, all biological systems have a limit, right? We're gonna find a limit if you have enough high levels of your input, in this case, seeding rates. A difference here that I just want you to realize is with the quadratic. So what happens a lot of times, it does happen with seeding rate, it happens with fertilizer, it may happen with other things that I'm not familiar with, and I don't want to speak for all of it. But what happens here is, in this case, your seeding rate on the quadratic response is just as we were talking about before. You're increasing number of plants per area, and then you're increasing the yield of that area to a point. And then after that point, you're adding so many plants that competition is so high that now the yield of that whole area is starting to decrease. That's when you would see a quadratic fit be the best, because it really represents that optimum, and then after that, it starts decreasing. We see this with seeding rates, we see this with fertilizer. So if you apply too much fertilizer, it may actually be you may have a too high of a salt index in that soil that now plants have a hard time taking up water because there's so many salts because of that fertilizer, and they start decreasing rates. Or maybe for other, everything in life, there is a balance between being something good or bad, right? Maybe you're creating a toxicity environment if you apply too much fertilizer. Then now plants are also not being able to handle those potentially toxic byproducts of that fertilizer and its reaction in soil. So there's always something that's going to be limiting at some point. And if it starts becoming then having a negative effect, that's when you see a quadratic response being the best. So my question, it could be to Shakir, or to anyone else, if you want to step in, is if you see the quadratic response on a grower's field, what would you say would be the best seeding rate for that field?
90.
Around 90,
90.
right? Yeah, so that's right. It's kind of somewhere around here, it looks like. That would be our break point. I agree with that. All right. Yes, Sabir.
I have a question. So, in case maybe you are writing, a manuscript, and then let's say your quadratic curve plateau at a seeding rate or a fertilizer rate that you've not tested. For instance, maybe looking at this one, maybe you've not tested 90, but your curve plateaus at 90. Can you report a seeding rate or a fertilizer rate that you've not tested?
Absolutely. And that's a great question because I think it connects here the difference between ANOVA and regression. So if we were interested on the mean yield at each level that we did observe, that we did apply to that study, then ANOVA would be that. So imagine that instead of having a line like this, you would have at each level that you did apply a given seeding rate, you would have a box plot. So instead of a regression, imagine a box plot at different levels here. And then you could compare the mean yield response at each one of those seeding rates. So maybe instead of having a regression equation, like a quadratic equation to go off of, you would have ladder separation, right? It can still be, again, if you're interested in the mean effect, you can use ANOVA in this case. But we are trying to find, just as Schwaber was asking, we're trying to find a level that may not be exactly one of our levels, right? We're trying to find an input rate that may be in between two of the rates you applied. And regression is then useful for that. Yes, thanks, Schwaber. Yes.
Does it have like a confidence interval?
Yes, absolutely. So Charles was asking here if whenever we find the optimal seeding rate, if that has a confidence interval. So the models we're going to be using will basically be, they're going to give you a point estimate, but then we calculate confidence intervals around that. And that's a great point because, although we need to have that point estimate, but it's also really important to be aware of how variable is that, right? Awesome. So now lastly here, if we observe a linear plateau to be the best model for a given data, it basically means, okay, you had enough input rates to find an optimum. Maybe you did not have high enough to really see a negative impact. So you kind of like reaches this optimum, and at least with the data you have, you kind of stabilize at that level. You don't see the downward side of that, like we did with the quadratic, which is also something that we see a lot. That would be one of the best fits if that is the situation. So maybe somebody else that hasn't helped me yet, if you see a linear plateau, what would you tell to that farmer? I see Tifton raise their hand. Yes, Tifton.
I would advise the 80. sitting right.
Absolutely. Thanks, Paulie. That's right. So 80 right here is where it seems like that breakpoint happens, right? So that's what we would say is the optimum rate. Perfect. So the thing is, most of the time, or at least from my experience, maybe on your area is going to be different, but from my experience with the data sets that I work with, that I do this, it's not as clear. Like you don't have this beautiful points just waiting for a regression to go right through them, right? It's like it's a little bit more messy and more like of a cloud of points rather than a very clear pattern. So then the way that we determine what would be the best model for a given data set is just running different models, seeing which one is the best fit for that data, using that model to then give a recommendation. That's what we're going to be doing today. All right, so this is the point that we start coding. So I believe that you have all, well, maybe not. Let's just do as normal. Like try to go and run individually each line of this chunk. If you find one that it says, I don't have that package, just go ahead and install it. I am anticipating you don't have NLRAA, so I left you the installed packages for that. And I'm not sure if you have Metrica. But the others, I believe you should have already at this point. So just going to give you a quick moment here to check on your packages, and then we're going to start coding.
Dr. Bastos,
Yes,
can I ask a question?
sure, go ahead.
Are we gonna do response surface optimization, or is it gonna be just fitting a model that has highest R square?
So a response surface type of model would be when you have at least two inputs impacting one output, right? So in our case here, we just have one input, which is student rate. But if you had a study where you had done maybe, well, if we had used our previous data set with nitrogen and potassium and the effect of that on yield, then that would have been a response surface type of model. But that's not what we're doing here.
Right, thank you.
Thank you. All right, so I'm assuming you're all able to load your packages. So let's get started here. First thing is let's bring in this data set. So this is a CSV file so on your file system. So we're going to use read_CSV for that. Open and close quotation marks, get outside of code, go inside of data, and then bring in your reg.csv file. You should see that object pop up on your environment, and then let's just print it to take a look at it and see what it is. So this is a table. It has 20 rows and 3 columns. So really here what we have is 20 observations that they're coming from, let's see here, we had 4 reps. So this was an RCBD, so 4 blocks, and we had 1, 2, 3, 4, 5 treatments. So 5 different seeding rates. And then in the end, we observe the effect on yield expressed in megagrams per hectare. So this data set is pretty simple and concise. It's not, so we don't have a lot of things to change here. I do want to change a few though. So one of them is going to be, well, let me take one quick step back here and tell you. So in the past, we had a full chunk dedicated to wrangling, which is completely fine. I want to show you here that if you have very light wrangling, maybe like 1 or 2 things you want to change about this data set, you could do that straight off after your read CSV if you wish. Assuming that also your read CSV is a relatively small file that does not take a minute to load, right? You wouldn't want to be running this every single time you want to do wrangling if it takes long to run. In our case, it's a very simple CSV. So I just want to add a pipe right after that read CSV. First thing I want to do is use the function clean names just to get all these names standardized. This again, it helps us when coding, if things have uppercase, by having everything lowercase is just a couple of hits on your keyboard, caps lock key, just a few less. So it's something that I normally do just for consistency and ease of coding as well. And then finally, I want to do something very quickly here, which is to turn our rep into factor, right? So even though our y and x variables, so y being yield, x being incident rate, are numerical, but our blocks are still categorical. So we want to just change that using a mutate. I'm going to call rep equals, use the function factor rep. This is a great simple question for an exam. What function would you use to transform something from numerical to categorical? Because we're going to need that, and we've done this every single exercise. So just a quick example of something I could ask you. All right, so if we just run that, and then we just print, again, this object, now we see the rep is factor, and then sitting rate and yield are numerical. Great, that's what we wanted, that's what we need for this analysis. Again, on our previous exercises, we needed our x variable to be a categorical variable as well, because we were doing ANOVA. We wanted to know the mean effect of a given sitting rate, or in that case, fertilizer rate on yield. Here, I don't want to know the mean effect. I want to know the response type, or the response formula that best fits this data. Okay, so this was an RCBD with 4 blocks. We have 5 treatment levels. So another thing that I want you to be aware, I think I say this, but maybe I don't emphasize enough, so I do want to take a moment and do that right now. Every time you're explaining your design, you're going to have treatment factors, you're going to have treatment levels. Those things are different. Our treatment factor is sitting rate. Our treatment levels are 40, 60, 80, 100, 120. Right? Make sure you understand that nomenclature. It's very simple, but it's something that you need to know when you're describing your study in your papers. And then here, so we have 1 treatment factor, sitting rates, and then 5 treatment levels associated with that, which are sitting rates that go from 40,000 seeds per hectare, 60, 80, 100, and 120. All right, so as always, we do some EDA to check that everything looks all right. So right now we have really the one that we would perhaps be more interested in this case is the statistical summary on yield. So ranging from 7.8 to 15.6 megagrams per hectare. And then we're going to do some plots to look at this relationship. So let's, I guess there are different ways we can check this raw data. I want to propose that first we do a box plot. So if I asked you, how would you do a box plot with the functions in ggplot that we've done until now? Can somebody help me with the code? I saw a hand come up, but it went away, so I'm not sure who that was.
Yeah, I mean, I was missing something in the like in the previous chunk. So
On this one here?
yes, I'm good.
Yeah, awesome. All right, so let's see. Let me ask Comfort, what do you think? How would you, if I wanted to explore a ggplot, or sorry, a box plot to look at the distribution of yields, how would you start this code?
ggplots, then we introduce our data.
So data.
And then, yeah.
GFW, perfect. If y'all want to code along with us, please do that. Okay.
Do I continue?
Yes.
Oh, okay. I think the AES, the aesthetic. Then we set the X first, which is the seeding rate. Then the Y is the yield.
Okay, I'm just typing as Comfort is saying, and then Y equals So the variable is yield underscore MGHA. Okay, so if we just run that, then this is what we get. And then if I want a box plot, what do we do?
you put the plus, then the geom box.
Perfect. Awesome. Thank you, Comfort. Okay, so if you run that, then this is what we see. What is going on here? Why are we seeing this huge box plot going across the x-axis?
Because it is teaching nitro this seeding rate as a like a numerical variable, not a factor.
Yes. Who was that?
Ashbin.
Ashbin. Perfect. Thanks, Ashbin. Yes, that's exactly right. So the reason why we're seeing this huge box plot here is because seeding rate is numerical. So the same way that we wouldn't ask for a mean from it because we're doing regression, ggplot also thinks the same way. It's giving you a whole box plot because you're not asking for the means of treatments because the treatments are numerical. If, let's say, if we were interested in the means, then I hope you figured that we would have to treat up here in our quick wrangling, we would have to change seeding rates to a factor. If we had done that, if we were interested in means and therefore using ANOVA and we're doing EDA, I'm just going to do a quick on-the-go change. You don't have to do on your side because this is just to show you. But if we treat just on-the-go seeding rate as factor, now we get a box plot for each seeding rate. However, this is if we were interested in the means of the seeding rates, and therefore we needed to do an ANOVA. We're not. We want to know the overall response. So even though this is just EDA, there's nothing wrong if you looked at it that way. However, that doesn't necessarily show you the data the way that you're going to analyze it. Neither does this. So how would you fix it? I mean, how, and by fix, I mean, what other geom would you choose to visualize this data in the way that you're going to model it? So if you come to the next chunk here, I left you the scaffolding, but we need to change the geom here to visualize the data as we're going to analyze. Did you say something, Trishman? Okay, sorry. Yes, Usman. Okay, geom point, right? So let's begin with that. Let's just type here geom point and then run it. Yeah, geom point, right? This is what we want to see because we're going to be fitting a regression line through here, right? And not a box plot, or we're not interested in the mean effect. Something else that is really, really useful, we have used already, and I just want to show you a different application of that when you're doing EDA, is to add a trend line here, right? So does anyone remember what function we used to add a trend line in the past?
Geom line.
Oh, okay, so we could, so that's a good point. So really the answer is geom smooth. But you could think geom line. Let's try that and see what happens. So if we do geom line here, this is what happens. So geom line is connecting every single point here, which is really not what we want, right? So geom line has its place, has its use, but here really what we want is geom smooth. So I want to show you here, we used geom smooth when we were looking at residuals before. So if you want to run geom smooth, this is what it gives you by default. So it basically gives us this smooth fit because by default is running a LUS type of function behind the scenes, which basically just says that is allowed to be squiggly. You don't have to specify the exact shape of geom smooth. It's just going to try to be squiggly so you understand the pattern of your data. And behind the scenes, there is a model being run, but we're not explicitly saying that model as we're going to do when we get truly model this data. So geom smooth does some modeling behind the scenes, shows you the output, and that's it. And then also gives you this error band around that fit. All right, so EDA, this is where we maybe confirm some of your hypothesis, or not confirm, but maybe have a point to reflect if your initial hypothesis were actually observed on your data. Not statistically yet, because we have not run a model and looked into significance levels, but at least visually. How would you interpret this plot? Yes, Omar.
So I would interpret this as the quadratic plot because the yield is dropping in the end.
I agree. It looks like quadratic is going to be the best, right?
Yeah.
I also agree with that. Now, what we're going to do, well, okay, let me take one moment here and ask, let me see. Let me ask somebody here. Karishma, let me ask you this. If you look at this plot, how would you at least interpret it with words? Like, what would you say here?
After 100 seeding rate, we can see the increase in yield. After that, if we put more seeding rate, we can observe the yield starts decreasing. So maybe the optimum seeding rate would be 100.
Okay, perfect. I like that. Awesome. And I'm going to be prompting you to also think on your side. I'm not going to be able to ask everyone, but to be thinking of, we're making all these plots because we want to understand what's going on, and understanding comes from you telling me what's going on, interpreting the plot. Just like we were interpreting with the box plots and the ladder separation, this is also part of interpreting when we're running regression. So make sure that you are able to interpret these plots and describe what you're seeing there. All right, so now this was a quick EDA as well. We don't have a lot of data to really look into different ways and partition in different forms. So this is basically the extent of our EDA for this exercise. So now let's begin by fitting our models. As I told you, I am proposing that we fit 4 different models. And again, there are more than just 4. I think these perhaps in my area of expertise are the 4 most common ones. In your area of expertise, there may be other ones. There may be some that that in my area are not even used. So be aware of that. I'm showing you some examples, not to say that these are all that you can do, but to show you some examples for you to get the idea and then be able to learn yourself, whatever is applicable to your expertise, your area of expertise. Okay, so we're always changing that options for set to, or sum from set to 0 to sum to 0 contrast types, which again, we don't talk much more about that besides it's just the way that the matrix algebra behind the scenes is going to parameterize our model. I want to propose here that we use the function LMER. The reason for that is just to keep consistency across all these models. And so if we're going to use LMER here, this is going to be really interesting actually, because it's simple, but it's a very nice place for us to understand this. So really on an intercept only model, that basically means there's no X variable. There's only a Y variable, and that's all. So let's start typing our Y variable here is yield underscore megagrams per hectare, explained by, if this was a fixed effect model, you would just say explained by 1. And that basically tells the model to calculate an overall mean, which is the intercept. In our case, because we're using LMER, I cannot just do this. LMER is going to say, where is my random effect, right? Remember, LMER is for either random or mixed effect models. It's not for fully fixed effect models. So here what we do then is we're going to give our random effect of rep because it is a randomized complete block design. Then finally, we just give our data argument. So data equals reg underscore DFW. If we run that, and then we get a summary of it, this is what we get. So we have our random effect related to blocks. We have our residual variance related to that EIJ of the model, that residual effect. So it is really interesting because this model is a random effect model. There's the only fixed effect is the overall mean, which is implicit here. If we just said +1, that would be this, it would have the same effect as not saying the +1, which is basically just telling, I just want the overall mean, which again, the overall mean is your intercept. That's basically it. Check the summary again. So here we see that the estimate that we get for the intercept is 12.174. This is the overall mean. This is the intercept that is calculating for us here. That's that value. Although the plot I'm showing, I don't remember, maybe it may be from the same data, but I mean, no, it's not from the same data. This is not the pattern we have. But it would basically be that intercept on the y-axis. Come back to it. So as always, we're gonna check for residuals. And today I'm really excited to show you some residuals because we're gonna see some weird residuals at some point. And we're gonna see one way to fix residuals. Not all of them, but one way. All right, so I just left you the code because you've already seen this. So we're just doing the augment to get the model fit metrics and then created a standardized residual. We're using a different function here. It's called resid. Before we used, I think was st-resid or s-resid. There's a little bit of a different function just because the types of models we're running, this is the type of residual that will work. But notice that we're getting the Pearson residuals and we're asking for it to be scaled. This is the key here, which is the studentized residuals, which is what we've been using until now, is one of the normalized residuals that we can use. Using normalized residuals or scale residuals like we're doing here is important just for us to be able to assess outliers. If you remember, if you do not scale your residuals, then that y-axis on your residual plot is going to be at the same scale of your response variable. So you're not going to be able to say 3 minus 3 are my thresholds. So we're scaling for that purpose. So let me see. I'm just quickly going to run here. So this is basically our data frame with the same variables as before, and now we have all the extra residual metrics as well. And I did a left join here. I don't remember why, but I'm sure there is a reason. Let me do that and run it. Okay.
Excuse me, Professor.
Yes.
Could you please repeat this part again? Like, why did you add type Pearson?
Yeah, so if we use the same function as we use it on the previous exercises, which was I think it was like rstud, I think was the function, the
Yes.
size residual. That function does not work with one of the models that we're running today. And for consistency's sake of these functions we're running today, the resid function does work with all of them. And then I'm just asking for that to scale. I guess the main thing is just to scale them. That's the main key takeaway. Okay, so
I also remember from previous exercise, like we added none in type, I guess.
I think you're thinking about CLD function, which is not what we're doing here.
Okay, sorry.
So
Sorry about that.
we said the adjust none when we were getting the means, and we were saying that
Yeah.
we don't want any adjustments. So we're not even
Mhm.
using that function here today. Yeah.
Sorry about that.
No problem. Okay, so I guess after running the left join, I did realize why I did it, and I want to tell you why. So if we just run until before the left join, we get yield, we get the rep, and then we get the fit metrics. What is missing here? Seeding rate, right? The reason why augment is not giving us seeding rates is because augment is based on the model, and this model that we ran has no seeding rate. It's just the overall mean or the intercept model. So I did a left join here just to bring back the seeding rate column into this data frame. So if you let that left join run, it's just basically going to look at the yield and the rep columns, and it's going to say, okay, for this yield and rep column, based on this data set we're doing the left join with, then this was, or let me run it all. This was the sitting rate associated with that. So it's basically just doing that. It's bringing back sitting rate based on known columns between both the data frames. So that's why I was doing the left join right there. Okay, so now that we did our residuals, or we extracted our residuals, let's plot them. So the first thing here is going to be to look at our within group errors and check that assumption. Remember that this is what kind of sets the assumptions that the model has. I left you all the code there already, so we're just doing that fitted by standardized residual, adding the a horizontal line on the 0, and then adding the points, and adding the smooth line. Okay, so this is how our residuals look like. We're clearly seeing a pattern here, right? We're clearly, even though there is, the 0 is confined within the error bar of this geom smooth, but we're still seeing this increasing pattern on our residuals. Yes.
I'm just curious about all the warnings we got. Is that something to expect when we get residuals that could interfere with our data and those are see, or something we did coding?
So these warnings are all related to geom smooth. It's just because behind the scenes, geom smooth is trying to fit this, and it was just telling us, hey, there's some issues here, but it's just for visualization purposes. So I wouldn't worry much. It's just telling it that it's having some issue trying to fit this curve. Yeah, but you wouldn't have to worry about it because we're just on the visualization side. So I want to tell you what's going on, but I want to first give you the chance of thinking what's going on. Why are our residuals increasing? So as you increase your fitted value, which is what your model is predicting, your residual is increasing as well. Absolutely, that's exactly it. So Micah said here that the model is basically under predicting. Is that right? Or am I getting confused as well? Well, you know what? For me to not say something that confuses you, let's just go to the next chunk where we're actually going to visualize this. And then we're going to be able to say without me or you getting confused. So residuals looking weird. There's this increasing pattern. Now let's try to understand why that is. Or before we get that, let's do a QQ plot as well, quantile plot. I left you the code already as well. So if I was just looking at these QQ plots, although we see the details are a little bit off, I would still not think this is horrible. Really what tells me that these residuals are suspicious, at least, is this. And then we also check our random effects. I left you the code there as well because we had the random effect of block. So you can just go ahead and run it. And we're going to print it. Again, just looking at this plot by itself, it does not look like there's a huge problem. All right, so now we really don't have an ANOVA, although I left that here perhaps for you to understand that now regression is what we look into summaries. ANOVA, we look into the ANOVA table. So regression, you know, we saw this before again. Something I want you to notice is, so we get our estimate of the intercept, and it is highly significant. I want you to bring this up and really talk about this for a second, because just because something is significant in your model, it does not mean you have a good model, as you're going to see in this exercise. So remember that significance in your model, and especially in this case that we're playing around different models and trying to find the one that best fit this data, significance alone is not what is going to tell you that this is a good or a bad model for your data. So it's highly significant. But now, is it a good model? Let's see. So what we're doing here, I left you the code as well. We're doing ggplot, putting sitting rates on the X, yield on the Y, and adding the points, just like before. Now, let me see here. I think we have some work to do on this chunk. Let me just come back. Yeah, okay. So what I want to do here is something we have not done yet, but I want to show the regression line that we use on this intercept model on this plot. There are different ways of doing that. I want to show you one of them at this point. So in our object where we augmented, which is this one here, where we have all the different fit metrics coming from augment, this column called fitted, or I'm sorry, the column called fixed, dot fixed, is the one that actually has our regression line. So we're just going to use that for our benefit and just use this column to plot that regression line. So let's come here. I want to add a geom underscore line where we need to change. So the AES coming to this point is basically whatever we specified on ggplot level. So on the X is sitting rates, on the Y is yield. Now I want to change what goes on the Y for this geom, which means I'm going to have to say AES again, and just change the Y to be the column dot fixed, which is a column in that data frame coming from the ggplot call. So if you run that, that is basically the regression line that the model fits to our data. Clearly here, we can see that, well, I guess we already knew that this was not going to be the best model. And now we can visually assess that truly this model does not fit our data the best. So what is a residual? Residual is basically the distance between the observed point, which is our points, to the line that we're using to model that. So here we have negative residuals, or not, sorry, not negative, but lower residuals up until this point, really, because all those points are lower than our regression line. And after the 60,000 seeds per hectare, most of the data points are above the line. And so we have that increase in residuals. So normally, if you see a residual that looks like this, it probably means your model is not properly specified, which in this case, we know this model is really other models, as we're going to start fitting and looking at the residuals, you're going to see that they're going to fix the residuals for us. So one way that you can potentially improve your model and therefore your residuals is by specifying the most appropriate model to that data, which then comes back to you visualizing that raw data first. In our case, we're going to run all 4 models regardless, because I want to show you and teach you how to do that. But maybe if you just looked at this relationship, maybe you were sold already that your model was quadratic and that's what you did. It's not common to do that because let's say this normally you would have at least a couple of sites, maybe a couple of years. So you would do that exercise of 4 models for each one of your sites and years, because maybe the relationship is different from one site year to the other. So you would still fit all those and then use some metric to choose the best model for each site year. But yeah, I guess just making the point here that our residuals in this case are looking weird because our model is under-specified. We know that we should add at least a slope to this model and not just have an overall intercept model. Yes.
Can we say that our model is not able to like predict which is the most important variable? Or is it because we have a few data points?
Okay, so Amandeep here is asking if with this we could say that our model doesn't have enough variables that would explain yield. It's going to be interesting here, Aman, because what you're going to realize is really the data that we have is this. What we're going to be changing is the model. So now the data is going to remain the same. Well, I guess maybe let me take one step back. So really in this model, we did not add seeding rate. We're just getting the overall mean, right? So to go to perhaps answer your question specifically about this model, yes, this model is missing the seeding rate effect, right? But that's it. Then after we bring seeding rate, then we're gonna be changing the model. So are we allowing seeding rate to change linearly, quadratically, or in a linear plateau way? And then all that is about the model and not as much about the variable, because the variable is still, we're just going to have seeding rates. Just how the model then uses seeding rate to explain yield.
above graph. So why yeah, here, like some of the values they are like they're getting from zero,
Mm-hmm.
like going in minus like negatives.
Mm-hmm.
So like how we predict, how we see that, like.
So, okay, so let's just revisit that concept. So if you see every point here that's below zero is because that point is below the regression line. So the residual is the difference between what you observed in your field and what the model is predicting. What the model is predicting in this model is just a constant yield, which is our fit, right? It's just the intercept model. And every time you have a positive residual, it's because the residual is greater than what the model is predicting. Nice, thanks. All right, so we just checked one of our models. One of the things here is that sometimes with simpler models like this, it would not be too difficult to get a error or a confidence level around this regression line. But some of the models we're going to be running in this exercise are more complex and will require that. And so I want to show you how we can do that with Bootstrap. I know it's 10:38, so you've been here with me for over an hour. So I want to give you a 5-minute break. And then once we come back, we're going to do Bootstrap. And I would believe at least one more model for today. And then we'll finish this on Tuesday. So yeah, let me give you a 5-minute break and then we'll come back. Let me just put a timer. Scroll down. So, or scroll up for me. Yeah. Is it one?
Dr. Bestos,
Yes.
can I ask you a question real quick?
Sure. Go ahead.
So you mentioned that the midterm exam will be covered up till the split plot design, right?
That's right.
Got it. Thank you.
Yep. If it was, let me see. Yeah, if it was a reading material, yes. I guess I don't understand what. Oh, yeah. Yeah, no, that's well, that's what I thought was important, but it doesn't mean I'm gonna ask you because I'll highlight it. Yeah.
Dr. Bastos?
Yes.
Yeah. Can you please go to the code where we had the box plot?
The box plots. Well, I think
Thank you.
the box plots was here, right? But
Okay.
yeah.
So we have a code. I didn't get the box plot didn't appear, so I don't know. But I think I have all the code. Let me just screenshot the code and then have time to look at it.
So if you're having issues, I think I would say check that your commas are there, check that your parentheses are closing, and that you have the plus after here. Maybe those would be the main.
Thank you.
So it's exactly.
Dr. Bassett, for the split plot randomization assignment, since you asked us not to delete any of the hashtags for the subheadings, is it fine to leave any hashtag that the subheading is kind of weird? Because there's a part where it says code, but there's literally nothing we have to put under the chunk. So it's labeled as a 5.3. Meanwhile, the next chunk where we actually have to write the code for the O plus randomization is labeled 6. So I don't know if that's
Um,
professional.
so I understand the overall idea, but I guess if you could share with me maybe like on GitHub, like a screenshot of what's going on,
Oh, okay.
then I'll be able to comment
I'll
on.
do that.
All right, thanks, Comfort.
Take hold of the song. And then right there. I did.
All right, so our time is up. Let's return here. Okay, so one topic that we're going to be covering now, and I don't want to get into a lot of depth again on this because it's something that is like a tool in your toolbox that you're not going to be using every time. And I want you just to be aware of it and show the code. And if you're interested in learning more and applying, you can do that on your own time. But so basically here, what I want to do is, so from the modeling itself, the modeling function itself, it does not give us an error bar or an error ribbon in this case around this regression line. And I want to do that. One of the ways to do that is to do bootstrap. So bootstrap, if you are not familiar with it, is basically we're going to create a fake data set that as far as seeding rate goes. So we're going to create all of these different levels of seeding rate and then give that to our model. And do, so bootstrap is basically resampling with replacement. So what that means is, so if we give it 1,000 points, it's gonna resample of a given size. And whatever resample is taking from those 1,000 points, those points can be, the resample points can be repeated in the sense of, for example, if I give it 1,000 points and I say, take a subsample of 50, you're gonna randomly pull a subsample of 50, but every time you pull the subsample, it can do a resample of the same point more than once, I guess is what I'm trying to say. So imagine, let's do a simpler example here. So if you have 10 data points, and I want to do bootstrap with that, and my bootstrap samples would be of the same size. It's going to be 10 data points as well. What the bootstrap sample is going to do is it's going to pull 1 point, let's say sample number 2. This is the first one on my bootstrap resample. But then it kind of puts back that opportunity of sampling number 2 back into the main hat. So now samples again is going to be sample 5, and then 6, and then 7, and then number 2 comes out again because you kind of put that back into the options of resampling. That is resampling with replacement, which is what bootstrap is. So what we're going to be doing here is we're going to create a fake data set of a lot of seeding rates, more than what we observed. We're going to give this to our model, and we're going to say, do a bootstrap resample with this data. So pull samples that were in a given sample that we're doing, we could have the same observation happening more than once. We could have some observations not happening at all. And in each one of those resamples, refit the model and do this for 1,000 times. with that, what you're basically doing is you're just creating some different realizations of your observed data. And then you're fitting a model on each one of those different different realizations of your observed data, and then extracting the coefficients from each one of them. So now instead of having one intercept, we have 1,000 times that intercept. And then we use that 1,000 realizations of the intercept to calculate an error bar around it. That's basically what's going to happen. I know it's maybe too complicated just to explain words, but that's what we're going to be doing next to create that error bar around this regression. Yes, Shakir. I can hear you.
Sorry. Is this considered to be a simulation of some sort? Since you are resampling and restructuring the model, continuously up to a given point, like 10,000 or 1,000 times. So is it a simulation of some sort?
So, I mean, I guess the answer to you, the quick answer is I don't know if that would be considered a simulation because we're not simulating new different values. We're using the levels that we see in our data and then simulating, well, sorry, I don't want this to get too complicated. I think we could call it simulation just because we're going to give values that are not observed in our data, but it's still values within our data, right? So it's not like we're simulating something that we haven't seen. So from that perspective, I guess you would say it could be a simulation. But really the way you would explain it is that you're doing a bootstrap resampling on the data. That's the word that you would use. And then the conversation of whether or not that is a simulation, I think is not one that you would use to explain what you're doing.
Got it. Thank you.
Awesome. Thank you. Okay. So I know that, this concept, I mean, it would probably take a whole class of exercises for us to talk about this and really dissect in a way that you fully understand it. So I don't expect you to fully understand this. I just want you to have an initial idea of what we're doing, and then you're going to see the code, how we're going to implement that in the code. So with that, the first thing that we're going to do here for that to happen is we're going to create a data frame that basically has a lot of sitting rates between our minimum and maximum sitting rates. I want to call that ND for new data. So we're going to use the function data.frame. The column I want to have here is sitting rate itself. So sitting rate underscore KSHA, which is the same name that we had in our original data frame that we trained the model. And for this, I want this to be a sequence of numbers where it's starting in 40, which is our lowest sitting rate. It's ending in 120, which is our highest. And I want at steps of 1. So it's going to basically give us a sequence of values from 40 to 120 at every 1 unit. If you run this and you print your ND, this is what we get. It's just a data frame with 1 column sitting rate, and it has 81 points here that go from 40 to 120 in increments of 1. We're creating this data frame here because we're going to be using this for doing bootstrap for all models, including this one here. All right, so the first thing I want to add on top of this NG, so if you come on the next chunk, is going to be to create the simulation. So here's what we're doing initially is I want to give all these sitting rates to our model and ask the model what is the yield that you would predict. Now, and again, the model we're working with at this point is this. So we're basically, instead of having just these values of 40, 60, 80, and so on, we're basically going to give it a sitting rate point that is all the way from 40 to 120 at every 1 step increase, and ask, what do you predict is the yield? That's what we're going to do in the next step of this bootstrap simulation. And just to ask you, so what do you think is going to be the result? Before we actually do it, what would you expect that this will predict? As far as what will the model predict is the yield for each one of these sitting rates that we're given, for all these 81 sitting rates from 40 to 120 at every 1? So imagine a new column here saying predicted yield. What would that be based on this model?
The intercept.
Perfect. The intercept, right? Because this model here really does not even consider seeding rates. It's just an overall mean model. And so the model is just predict, regardless of seeding rate, is always going to predict that same intercept value, which is this value here of 12 point something, that, as Shay was saying, is the intercept of the model if you go back to the summary. This value here. It's going to predict this value pretty much. All right, so let's do that here in this next part of the chunk. So we're going to start here with ND. We're basically going to overwrite ND. So we're starting with ND, doing something and overriding on the same object name. We're going to use here a mutate because we're creating a new column. I want to call this mod1 underscore yield underscore MGHA. And then the way that we get a prediction for each one of those points that we created here for all these seeding rates is going to be using a function predict. So here, the first thing we give is the model that we want to use to predict. So the model object is named mod1 underscore int for intercept. The second argument is the object name where I have the X variable that I want that model to use to predict the Y variable for us. So that data frame is called ND, is the one that we created above here. And then because this is a random effect model, we need to specify at what level of the random effect we want to predict. What this basically, what does that mean in practical terms? It basically says that if I wanted to predict at the block level, which is our random effect, I also need to give a block information. So let's say I would have to say predict the yield for seeding rate 40 in block 1, which for prediction makes no sense because you're not going to have blocks out on the world, right? That's something you had in your study. So we need to say don't predict at the random effect level, predict at the population level. That's basically what we have to change here next, which is this argument for that's called re.form equals NA. So that's what we're going to do. If you so do not run the whole chunk yet, just run this part, and let's just print what ND is. It's basically what we just talked about. The model is predicting the same yield for every single seeding rate that I guess here's where we would say, right, Shakir? So we would say if we simulated different seeding rates that are still within the range of our data, and we're getting the yield response based on that model that we just did for each one of those. So this is not the bootstrap yet. This is just us giving different levels of seeding rates and asking for a prediction based on that model. Now, I want to walk you through what we're going to do next. The next thing, and I left you the code for that, is we're creating a function. We have not fully talked about how to create functions yet. This is coming up in, I guess, a couple of exercises. So if this does not make a lot of sense yet, don't worry, because you will learn more about it in a future exercise. But we're creating a function that is called predict.fun. Remember I told you that anyone can create functions and packages for that matter. A person creating a function, I mean, you can create a function without creating a package, I guess. This would be an example of that. We're just creating a function that the name of the function is predict.fun. It takes this object called mod as one of the arguments, and it puts that mod inside of a predict. So this predict function here is an actual already existing function. It's the one that we just used. This predict.fun function is one that we're creating, just that we're going to give predict.fun an object that the function is calling mod, is going to give that object to the predict function, is going to take the new data in ND and give you a prediction. So if you have your cursor here on predict.fun and you just run it, this is actually a function now. So it appears on your environment as a function that you have available for you to use right there. And we already talked about what the function does. So why am I doing this? So now the next step is really where Bootstrap happens. So we're creating an object. So we're not creating function anymore. That was the only function that we created. Now we're creating this object called mod1 intercept bootstrap, where we're calling the function bootmer, which is a function from the LMER package that does bootstrap on LMER objects, that we're giving our model. So mod1 int is the model. If you just print that, it's going to be our model that we trained. We're going to give it a function, which is the one that we just created above, the predict.fun, and we're going to say how many simulations we want. We want 200. I asked 200, so it does not take a lot of time. This number here could be higher, could be 500, could be 1,000, right? But this is where you would control how many simulations you have. After it does that, it's basically going to give us a... So this function here is where the actual bootstrap happens. It's going to do... I'll be with you in a second, Omar. So for 200 times, it's going to look into our data. It's going to pull a resample, train a model, extract the intercept. Put that to the side. Does that another time. Pulls another sample from our data, trains again the same model, gets the intercept, and stores that. And is doing that for the intercept, but also for each one of the observations in ND, which is used right here. So we're getting a prediction of yield from 200 models, where each model is trained on a bootstrap resample of the original data, and getting a prediction for each of the seeding rates that we're given here. Doing that 200 times, and then after that, we ask for a confidence interval around that. So imagine that now you have a confidence interval for the yield prediction of this model 200 times for each one of the seeding rates we're giving. And then that's what we use to create this continuous error bar around that regression line. So this is where the bootstrap happens. This is us getting the confidence interval. We then turn that into a data frame. And then I just renamed some of the outputs to be the 2.5% confidence level and the 97.5% confidence level for each observation that we're giving on ND. I know this is a lot, and I'm not doing this step by step with you because this step here takes time. So if we were building this whole pipe line by line, we will have to run this first step many times, and that would just delay us. That's why I'm giving you the whole thing and just saying what's happening. On your side, if you're interested in understanding what happens on each step, you're of course welcome to do that. You just add a hashtag at a given point, run until here, inspect the object, let it flow to the next one, stop the flow right there, run it, inspect the object, and so on. That's how you, on your side, you can learn what's happening in each step. All right, so I'm gonna run this, and I think it may take a quick moment, but while that's running, I think Omar had a question. Oh, actually ran it already.
Yes, Professor.
Yes, go ahead.
Yeah. So I was wondering, what would be a good number in your experience to run the model? Like you said, you added 200 for the sake of time in the class, but overall, what would be a good number?
I mean, I don't know if there's a really solid recommendation, but I would do between 500 and 1,000, I think would be a good number for you to get a better estimate of the variability of those values.
All right, thanks.
All right, thank you. Okay, so it ran all that. Let's just print this mod1 int boots, which is what we created just above, and inspect it. So now notice that we have 81 rows and 2 columns. Why do we have 81 rows?
It's that seed rate that we created.
Because we have 81 here on ND, right? So we gave
Yes.
81 new seeding rate values that we wanted a prediction of. So that's why we have 81 rows on the bootstrap results. So notice that we have a lower confidence level and an upper confidence level for each one of our 81 observations. The thing that's happening here, though, is we don't know yet. We don't have a column here saying seeding rate. So we know what seeding rate is associated with which one of these values. And we need to do that. So that's what we do on the next step. So we're overriding ND again, and we're binding the columns of the mod1 int boots, which is basically, oops, no, sorry, we're binding ND. So ND has just sitting rate, and then 81 rows. We're bringing the columns of mod1 int boots into that. So just bringing those columns and kind of connecting them right there. So if you run this and you print ND, now we have our sitting rate. We have the prediction of yield. So this would be your mean predicted value. And then we have the lower and upper confidence levels around that prediction.
Dr. Bestos,
Yes.
will everyone get a different results for the confidence intervals because my value doesn't match with yours for the upper limit and the low limit?
So that's a good question. So since we did not set seed, and this is a random process when it's pulling the resamples, you could get a different value than what I did. Probably if we increase and I mean, if we set seed and or increase the number of simulations, then our values would all converge to a more similar value. But because it is a random process of resampling, you could get a different value from mine. However, for this model at least, your value should be equal within that column, because that's what the model is. It's just an intercept model. So, okay, so let me just take a quick step back just to walk us through quickly what we did. We created this data frame that has seeding rate values from 40 to 120 at steps of 1. We then used these values to ask for a prediction. So this is what creates the mean prediction. And then we use a function for bootstrapping, and actually bootstrapped here to get 200 simulations of bootstrap simulations here, calculate the confidence interval, and basically just do some wrangling for that to look nice in a way that now we have the mean prediction coming from here, and also a upper and lower confidence around each seeding rate value that we gave the function to predict. That is what we need to create a confidence interval plot to show us the certainty around those values. So I left you the plot here already. We're just doing, again, a scatter plot, adding the points, and then I'm adding the line here, which is the line from basically that has the mean prediction. So if we just run here, this is what we have. This is that mean prediction value or prediction line. And now I want to add another geom here that is the error around this line. So I just want to print here ND for you to see again and walk you through quickly here. So seeding rate is all the values we simulated and gave the function. Mod1 yield is the mean response, meaning it is what the model is predicting, or in other words, is the model line fit. Then we have mod1 intercept LCL for low confidence level and UPL for upper confidence level. And now we're going to use these two functions to actually add those error bars on the plots. Sorry, not functions, these two columns. So if you come back to this code, add a plus. This is the first time you're going to see this geom, at least in this class. It's called geom underscore ribbon. Before I develop that, comfort.
Yeah, Dr. Bastos, when we run the code again, it seems like it's adding up more columns for the confidence intervals for me. Now I have 8 columns because I ran the code again.
Yes, okay, so that's something that's actually, now that I'm looking in retrospect, is a design fault on my side, which is, so Comfort is saying she has 8 columns rather than 4. What could have happened, Comfort, is because we're overriding on the same ND data frame, so we're creating ND here, but then we're overriding on it here, and then here as well. If you run any of these steps more than once, it's gonna basically do that step more than once and assign it again to ND. That's why you're getting a different number. So just to make sure everyone gets the same number of columns, make sure you rerun your initial ND. So we basically redo what we did. So run ND again, and then run. So don't play the whole chunk yet, but just run these parts separately. So this ND, the predict function is already there. You don't have to rerun it. You don't have to run again the mod1 in boots because that is not overriding on ND. You just have to rerun again this third ND here. So if you rerun ND on this step, and on this step, once each one, your final ND should be the same as mine.
Yeah, I saw that. Thank you.
Yeah, I'll be with you or Usman, just a sec. So this is just to summarize. This is basically, again, it's a design fault on my side. I should have actually named these objects a slightly different name each time instead of overriding. And I guess I just wanted to expose my own problem here because it's something that you may encounter on your side when you're doing your programming. So maybe let us all, including myself, avoid overriding objects. Yes, Usman. This one? Yes. Did anyone have any questions or thoughts at this point? All right, so if we come back here to our final plot, which is at the end of this chunk, where we're adding a geom ribbon. So a ribbon is basically a ribbon, right? And for that, we have to specify what is the minimum and maximum boundaries of the ribbon. So we're going to say here, we're going to have to change the data. So the data is not the one coming through the ggplot call. It's not going to be in reg dfw. It's going to be nd. So data equals nd. On the aesthetics here, we have to say that, so the y is still the same as what's coming from the upper call of ggplot. I don't think we have to say that again. It's still going to be, so nd, if you look at it, it has the column sr ksha, just like what's already on the x from the upper call of the ggplot. But we have to say what's our y min is a new argument here. Our y min is going to be our mod1 int LCL, is our lower confidence limit. Our y max is going to be our mod1 int UPL for the upper confidence level. Let's just try to run this and see how that looks like. Okay, actually, it did not work because we did not give it the, what is it? Let me see, my error here, object yield not found. Yields. So this runs. So it doesn't, oh, okay. So really the yield value is coming here because it's, so okay, this is really is an interesting point. Every time that we set up our AES at the level of ggplot, then these AES here are going to be applied to every geom you have afterwards. If you specify the level of the geom specifically, then it just applies to that geom specifically. In our case here, for ND, we do not have, well, we have the mean yield if we want it, which would be in this column, but we really don't need to plot it because I don't want to plot the mean yield. I want to plot the error around it. So just to make sure that we basically ignored, because here it's saying ggplot is telling us that y equals yield. You don't have yield in this ND data frame. So just to make sure that we get away with that and not having to specify, if you come outside of AES, there is an argument called inherit AES that is normally set to true. We're going to say false. So we're going to say for geom ribbon, ignore what ggplot is telling you to do. Here on the AES, just do what I'm telling you to do at geom ribbon. Then in that case, when we do that, it's basically going to ignore this y equals yield, but then it does not know what to put on x because we have not set it. We just said ignore what ggplot is telling you. So we need to come here and say x equals sr underscore ksaj. because we're ignoring what the ggplot level is telling us. So we need to repeat that here. All right, so once you run that, then this is what we see. That's our ribbon around the prediction. It's kind of ugly, right? It's not very, very informative at this point. So I want to come here and do a few things. One of them is I want to change the transparency. So let's say alpha equals 0.5. If you run it, then now it's transparent. We could stop here. Yeah, I think this is a good stopping point, at least for this code. So right now, this is the error associated with basically that intercept, right? This is the error of the intercept and with the prediction of that intercept across seeding rates. In this model here specifically, as we already talked about, there is no seeding rate effect in the model. That's why the error is the same across all seeding rates as well. It does not have to be like that. It could be that the error is different in different seeding rates on other models, as you're going to see. Not on this one, because again, seeding rate was not part of it. All right. So this is what I wanted to show you for this model. A few thoughts that I want us to be aware of. I think we already talked about this, but I have in text, so I will just repeat it. Is the p-value of the intercept was highly significant. That does not mean this is a good or a best model for this data. As we already saw visualizing it, that is not a good model. It's not doing a good job overall. So do not rely on just checking your p-values and saying significant, it's a good model. It's not. We have to check residuals. We have to check, well, I guess residuals in this case, but also plotting the data and the model result is what also helps you to understand that. Okay, so the next immediate complexity here would be to keep a model that has an intercept, but now to add a slope to it as well, right? So that's what we're going to do on the next portion of this code. We're going to do a linear regression with intercept and slope. So we change our options again, just to make sure that they are according to what we want. And then on this mod, now we're going to train that model and assign it to an object called mod2_lin. We're going to come here. We're going to use our LMER function like before. We're going to call yield_mgha, explain by, and then we have a tilde for that. We're still going to have our random effect of wrap. So one vertical bar wrap. How do we now add a slope to this model? What do we need to say here? So the slope of this model is associated with the seeding rate. The way that we do that is just saying plus seeding rate KSHA. That's it. That's what we need to do. Of course, we need to say the data. So give it a comma and let's say data equals reg_DFW. That's our data. So now this is it. Notice that every model, even if you don't ask it explicitly, is going to give you at least an intercept. And that's why in our ANOVA tables, there's always an intercept row. Now, as you start adding things here to this model, if that X variable is numerical, then it's going to calculate a slope for you. If that X variable is categorical, it's going to calculate a mean for you. Or I mean, still, yeah, the mean actually comes from e-means. It's not at this level. But if seeding rate is categorical, you get means. If seeding rate is numerical, you get a slope in this case. So if you notice the model, there's nothing different about this model that I'm saying in the model run a regression for me. We're still using LMER like we did for the ANOVA. We still have blocks as random as we did for the ANOVA. The difference is that our X variable of interest, in this case, seeding rate, is numerical. And remember that this is something that happens when R imports it. That's why it's important that if you're doing ANOVA, you need to change your numerical treatment factors to category, which we're not doing here because we're not doing ANOVA, we're doing regression. Okay.
Dr. Vázquez.
Yes.
So If we have a more explanatory variable, so we will do the same syntax like multiplying or by, let's say, like another factor, or it will depend if we have additive or
Yep.
interactions there.
So if we
Okay.
had more explanatory variables, so on a regression exercise, sometimes you may want all the potential interactions in main effects, and others you may not. So if you do want all potential interactions in main effects, you would just use the asterisk, right? But if you only want specific combinations of some variables, then you can do that, just adding the plus sign and then giving main effects. If you want interactions, specific interactions, you would just use the colon between those variables, and so on. Yeah, so the overall syntax is still the same. Okay, so if you ran mod2 and you print the summary, then so with the beginning here is still very similar, right? We still have on the random effects, we still have rep and residual. On the fixed effects now, we have one more line here. So we still have intercepts. One thing that's curious though, is notice that the intercept value that is estimated now is different from the intercept value estimated before. Right, so it does not mean that you add more things to the model and the previous things that were there will remain the same. Now that it's a whole different model, right? It's trying to do something else. And so the intercept is different because of that. Also notice that we have KSHA in this new summary table, and the estimate is 0.05. What is this? This is yes, comfort. Thank you. This is our slope, right? This is the unit change or the change in yield for 1 unit change in seeding rates. This is the effect that this model is giving us. And also notice that both of the intercept and seeding rate are highly significant on this, based on this side. All right, so we trained the model, or we ran this model. We noticed that they're both significant. Now let's get the residuals again. I have everything here for you. It's the same function as before, so nothing new here. We're gonna check our error residuals first. Look at this. Now our residuals look different. I mean, they still have a pattern. Sorry if for everyone that we have somebody, I guess, mowing grass right next to us or something. But so notice that these residuals now are different. And I think this is the point I really, really want to, get into your minds. Residual depend on the data and the model. That's why we check residual assumptions and not raw data assumptions. You can still check raw data assumptions if you want to say if it's normal or not or whatever, but that is not what is the assumption. The assumption is the residuals, and residual change depending on the model. So notice that we have the same data, but a different model creates different residuals, right? Because again, residual is the distance between what you observe and what the model thinks or the model is predicting to be. So, I maybe you remember what we saw before, but I just want to bring them side by side so you look again. These are completely different residuals based on the same data, just applying a different model. So remember, residuals is what we use to check assumptions because they change if you change the model, whereas the raw data does not change. Okay, so let me come back to that plot. Okay, so now the residuals, they look different, perhaps not better, right? So still there is a quadratic pattern here, right? And we're gonna see why when we make that other plot showing the points and the model fit again. But something that I want you to kind of think of is, again, one way of fixing your residuals is by fixing your model. In the sense of a under-specified model will give you hints of will give you hints on the residuals of what is that you're missing. So if we look here on these residuals, oh, where is it? So this is kind of telling you, hey, try adding a slope to your model and see if that improves. So we went ahead and included a slope to our model. And then we see these residuals. So what this is telling me is, hey, try to include a quadratic term to your model and see what happens. So we see a quadratic response on the residuals. That means that probably you're lacking a quadratic term on your model to fix these residuals. This is not the only place that, or only way that you would fix residuals. Sometimes you have the perfectly defined model, your residuals still have issues. But I don't want you just to understand that changing the model specification will always fix your residuals. That's not the case, but that is one of the cases where you may fix residuals of a model. So let's check our QQ plot. I left you the code. I don't think you have to do anything there. Now the QQ plot looks even worse than before, right? So really now we see these deviations on the tails. So normally the middle of the QQ plot looks all right most of the time, but the tails are deviating here. And I mean, I don't think it's like something that I would completely worry a lot if I don't have other pieces of evidence. If I'm just looking at this, I mean, it does not look the best, but it's also not the worst. I've seen worse. But but we know based on this plot here that yes, we have something going on we have to address. So it's different pieces of evidence that you get that your model is doing a good job or not. Now, if we take a look at the random effects of block, I left you the code already. You can just go ahead and run it. Again, we just have 4 blocks, so it's difficult to gauge. But if I was just looking at this, I wouldn't be worried. All right, so let's check again our model summary. So now the model that has a slope and an intercept, just to remind us, the intercept estimate is 8 and the slope is 0.05. I left you here the code for the final plot. Let me just make sure if I have other things that we need to do or not. Yeah, so I think here I left you just a scatter plot. So I want to add the fitted line or the train line or the line that is the actual model that was ran with this data. As before, we added a plus. We ask for a geom underscore point. I'm sorry, geom line, not point. Where if you check here the model to lin og, this is where we have the data and the fitted residuals or the residual metrics. The column that we want to plot is the fixed, just dot fixed, just like before. And this is what we want to go on our y variable. So AS y equals dot fixed. If we run it, this is our model, the model that was trained behind the scenes. So I want to take a quick moment here and tell you that if we go back to that summary, so intercept is 8. So what happens here, it looks like, at least with what we're seeing, it looks like it's not 8, it's like above 10 on the y-axis. What happens is this is the y-intercept when x equals 0. So really, one way that we could kind of see this is if you come back here, I want to change the range of values on my x-axis. I want to say scale x continuous. I want to say limits and give 2 values, a minimum and a maximum. So the minimum I wanted to change to 0 and the maximum I'll keep 120. So now we're seeing where 0 is. And if you were to project this line all the way to where x equals 0, then y, our intercept, is 8. That's why the intercept from the summary function is 8, because that projection would be on 8. On the previous model, it really did not matter because the intercept was the same regardless of the x variable, right? In this case here, we can kind of see that would be the intercept. And the slope here, so the slope of our summary is 0.05. This is the rate of change of yield for each unit change on seeding rate. So each one, in this case, it's not just one seed, is 1,000 because these values are in thousands, right? So 40,000, 60,000, so on. So for each 1,000 increase in seeding rate, the model is predicting a 0.05 megagrams per hectare increase on yield. That is how we would interpret your slope. I want to take a quick moment here and check if anyone has questions, problems. Jonathan, is everything okay?
I'm fine.
Okay. You having code issues?
No.
Okay, all right. Online, anyone?
Yes, I think I had some error in my code, like coming down, so I couldn't follow from there. I think it was from where we're creating predictions.
So the predictions are coming from the augment. I mean, we have not done the bootstrap for this model yet. I don't know if that's what you're referring to predictions, but so really, I guess what we're using here is a piece of chunk I left you already, which is this one, which is the one that has the augment. And you didn't have to write anything there. It was already there.
I think before this one.
Before this one, I think it was just the model.
Where we had final plot, the GG plot, where we have the forest green. I think it's up. Okay, yeah. Yeah, we have the final plot.
Wait,
I
no,
had
but-
some.
Well, so Sober, I think what let's just keep moving because we just have, well, we would just have 1 minute actually. But then we can help you out specifically to see what happened with the code, if that's okay. All right, so we just have a minute. I don't want to run late with you all. Let me just see where we stopped here. No, this is where we stopped. Yeah. So we just have one more chunk. I think because I already told you everything about this chunk, we can just go ahead and run it. We're just going to take maybe a couple minutes. So notice that we don't recreate ND because we already had ND. If you remember, ND had seeding rate, the model 1 predicted value, so the mean value, and then model 1 lower and upper confidence limits. Now we're just going to override that to have another column that's the prediction of yield based on the linear model. That's what we're just doing here. To run that. We're now running the bootstrap resampling predictions with this linear model. So we get a prediction of yield for each seeding rate from 40 to 120 in increments of 1. We're binding the columns again, so we bring those predictions of upper and lower with the mean prediction of the model. And then I think you already have everything there. You can just run the ggplots to inspect it. So this is the model. So the line is the model predicted value. The ribbon is the upper and lower confidence interval for those predictions. Here you see that the ribbon is not constant. It goes up and down depending on the uncertainty of the model in different places. Okay, so I want to stop here. 11:31, so we're a little bit after the time. Okay, so Amrinder has opened the attendance already. Make sure you claim your attendance before you disconnect. And then next class, we're gonna finish this exercise. And we may have 10 or 15 minutes if anyone has questions about your grades or maybe questions about the exam as well. Okay, if you get your attendance, you're dismissed. I'm gonna stop recording here. And I'm gonna stick around for another moment if anyone has questions.